the specific heat of iron, which is 0.44. I just realized I said nickel had that specific heat in the previous video. I think that was me. So iron is 0.44 joules per gram degree Celsius. For specific heat, we need to do final minus initial for the temperature. It's final temp and cooled, so its final temp was lower, 5 degrees. Minus its initial temp of 94, so it had a negative temperature change. It cooled off about 89 degrees. So that means it lost heat, so we're going to get a negative Q. I'm going to plug it into the Q span equation. So we have our mass in grams times our specific heat in joules per gram degree Celsius times our delta T in Celsius. So everything cancels here except for joules, which is good because that is our goal, is to calculate the joules of heat that's given. 34,000 joules were released. Alright, now we're going to get a little fancier. Okay, I talked before about how I'll be doing labs and doing reactions that occur in water. Okay, this is how it happens. Okay, the most common technique that we use in calorimetry is to use atmospheric pressure to keep the reaction at constant pressure. So this sounds complicated, but really it just means using an open container. We're going to use 2 styrofoam cups nested together to provide insulation, but we're going to keep our reaction at constant pressure by using just a simple coffee cup. It's also called coffee cup calorimetry. So delta H is the same as Q if we're at constant pressure. That way we stop our system from doing any work by keeping it at constant pressure. So our delta H is simply Q. So the easiest method is to use the coffee cup calorimeter, a simple styrofoam cup. So what you're going to do is place an object like a piece of lead or some reactants like sodium hydroxide and hydrochloride in water in a coffee cup. And by measuring the temperature change of the water, we'll be able to figure out what the piece of metal or the acid-base reaction did in terms of energy. So we're not even going to mess with lids. You just stick a thermometer in there. And I usually don't mess with stirs. We can just swirl the cup. It happens fairly quickly, so it doesn't take long. And you have 2 cups nested together for extra installation. So you can carry out reactions that happen in aqueous solutions, and also the hot metal placed in cold water. And that can all be done in a coffee cup, and we'll do both. And we can figure out the heat change of our system, of our reactants and products, simply by measuring the heat change of the water, which is kind of nice. Alright, so constant pressure calorimetry requires us to measure our system indirectly by measuring its surroundings, which in this case would be the water. And we know the specific heat of water is 4.184 or 4.186. I've seen it both ways. I just usually use 4.8. We can measure the delta H simply by doing a fuse mat for the water. Alright, so here let me show you an example of this. Okay, there's going to be 3 different kinds of calorimetry we talk about. The kind involving a physical mixture, like a piece of hot metal thrown in some water. The kind involving a chemical reaction in water, like an acid-base reaction. And then lastly, setting stuff on fire calorimeter. That's the one we're actually going to do. Okay, so say we got a 72-gram piece of metal, and it's at 100 degrees Celsius. And we put it in a coffee cup that contains 95 grams of water. It's pretty cool at 12 degrees Celsius. What's going to happen there is quite quickly, the metal is going to cool off. And it's going to lose heat. Where does all the heat go that came out of the metal? Well, into the water. And that's going to cause the water to go from 12 degrees up to 23 degrees. So the final temperature here of 23 degrees is the final temperature of both the water and the metal. Remember that. Okay, they come to an equilibrium here. The metal loses heat, and the water gains that heat until they are equal, and that ends up being at 23 degrees. From this data, we can figure out the specific heat of the metal. Alright, we don't know the specific heat of the metal, but we do know the specific heat of water. So we're going to figure out the water first, essentially. So So first I need to just read the question and try to understand what they're asking you. Can you just try to picture it? Picture a piece of hot metal being taken out of an oven and you're placing it in a cup of water, and it's going to lose that heat to the surrounding water until they're at the same temp. Okay, since the metal's hotter than the water, heat will be transferred from the metal to the water until they reach the same temp. T final is always going to be the same for both of them. Okay, the water and the metal. So we need to keep track of what our system is, what we're investigating, and what the surroundings are. Otherwise, this is going to get confusing. So, what is our system in this example? The thing we're investigating, that would be the metal. We're trying to figure out its specific heat. What's the surroundings? The water. So is the system losing or gaining heat? Well, it's a hot piece of metal and it's cooling off, so it's losing heat. It's therefore going to have a negative Q. Okay? Now, let's look at it from the surroundings point of view, from the water's point of view. Is it gaining or losing heat? Well, it's going to gain heat. So the water would have a positive Q because it gains heat from the metal. So this is the key right here. Remember this in your mind. Whenever you're doing calorimetry, you're measuring heat flow, right, from one substance to another. You're using that to figure out, in this case, the specific heat of a metal. The amount of heat that was lost or gained by your system is always going to be equal to the amount of heat that was gained or lost by the surroundings. The only thing different is the sign. Okay, so in order to figure out the specific heat of our metal, we're going to look at our surroundings, look at our water, and figure out how much heat our water gained, because that's exactly how much heat our metal must have lost. Okay, so you're frequently going to be figuring out the heat of your surroundings and then receiving the sign, and that's going to be your system. It's seldom possible to directly measure the system. So instead, we measure the surroundings, and just flip the sign. So this set all the numbers you know with the units and everything. So, the mass of our metal is 72, the initial temperature of the metal is 100, the mass of the water is 95, the initial temperature of the water is 12. The T final for both of them is 23 degrees. So, we also do another thing that's not listed here. We're looking for the specific heat of the metal, but we do know the specific heat of the water is 4.18. So right now, this is supposed to be a Greek letter. I forgot to change it to a symbol. What formula can help us? We can't just use Q's math for the metal because we're dealing with two different substances in this question. But remember, the amount of heat lost by the system is going to be equal to the amount of heat gained by the surroundings and vice versa. It's just the signs that are going to be different. So the negative Q of the metal is simply the positive Q of the water. So we Q's math the water, since we know mass is 4.18, we know the mass of the water, we know the change in temperature of the water. We get that positive Q for the water, and then we simply change the sign and make it negative. And then use Q's math again and solve for the specific heat of the metal. Just do Q's math twice. Now I'm lazy, I don't like to do things twice. I like to do things all in one step if at all possible. So what I do is set it up like this. The negative Q of the metal equals the positive Q of the water. So I'm just going to plug in what Q is. The negative SM delta T of the water equals the positive SM delta T. The negative SM delta T of the metal equals the positive SM delta T of the water. There you go. Okay. The negative SMAT of the hot object equals the positive SMAT of the cold object. However much energy your hot thing loses, that's how much your cold thing is going to gain. Okay, and we know this is the specific heat of water, and the water gave heat. We don't know what that is for the metal. So all we have to do is solve for this variable right here. So I always place the hotter substance on the left, the negative Q. In this case, the metal on the left, just for consistency, so it's easier for people to understand more. So the negative SMAT of the metal equals the positive SMAT of the water. Here's the specific heat of water, times SMAT, times its final and its initial temperature. That's going to be equal to the negative SMAT of the metal. So the positive SMAT of the water equals the negative SMAT of the metal. So S of the metal, we don't know what that is, so we're going to put out times the mass of the metal times the final minus initial temperature of the metal. So doing the math and everything, notice negative times negative, you can't have like a negative specific heat. Okay, the needs are a positive quantity. It's how much heat it takes to change the temperature of the group. So it worked out that I'm going to get a negative times a negative here, and a positive number. Solving for S, I get 0.78. That makes sense. Okay, metals have really low specific heat, so they're going to be small compared to the 4.1 that water has. Metals have very low specific heats, so we came up with 0.78 joules per gram degree Celsius. If you sit here and think about the algebra with all these units, it all cancels except for joules per gram degree Celsius. All right. Now, the next type of problem involves, instead of just a piece of hot metal getting dropped in some water, in this one, we're going to do a chemical reaction, like an acid-base reaction. These are a little trickier, I think. So here's an example. Suppose we mix 50 milliliters of 1 molar hydrochloric solution at 25 degrees Celsius with 50 mils of a 1 molar sodium hydroxide solution that's also at room temperature. We mix them together, and after stirring, the temperature has increased to 31.9 degrees. What's the delta H of this reaction? 8 kilojoules per mole of HCl. Whenever we're doing a reaction and we figure out the delta H, we need to focus on just one substance, like per mole of that one substance, because in this example, it's a 1-to-1 mole ratio between everything, so it wouldn't matter. But in other reactions, there may be 2 moles of acid and every 3 moles of base. And the delta H is tied to that coefficient, as we learned in the thermochemical equations section. So we need to focus just on one substance. Alright, so in this instance, it's really the same kind of problem as we just did, it's just the algebra is going to be a little different. This time, everything's in water. So remember, when you have a molar solution or some kind of acid or base, we just get to pretend it's water. So we can also assume it's going to have the same density of water. So it's going to have the specific heat of water and the same density of water. So altogether, instead of 100 mLs of solutions, it's all mixed together, I'm going to say it's 100 grams of water. Because it is. Okay, so for these, the Q of the reaction is just figured out by Q spent. Once again, okay, the Q of the reaction is equal to the negative S of water times the mass of the solution times the delta T. And then we have to put it per mole of one of the substances. Now, it's just a Q spent situation again. That part hasn't changed. What's changed is that we're not figuring out the specific heat of any one particular object or chemical. We're figuring out the enthalpy change of the entire reaction. So all we do is figure out the Q of the water, Q of the surroundings, okay? The water surrounds HCl and the NaOH and the salt and the water that gets produced. We just figure out the Q of our surroundings and change the sign. Once again, whatever the water gains or loses, that came from the reaction. So, in addition to doing chemical reactions, we can also just do this for stuff dissolving. That's called the enthalpy of solution. That's how you write it. It's just the heat that's generated or absorbed when a certain amount of solute dissolves in some solvent. For example, those disposable ice packs have ammonium nitrate in them, because when that starts to dissolve in water, it sucks in heat. It's an endothermic reaction. So it sucks in heat from you, the surroundings, so it feels cold. These two, the calcium chloride